this class anyhow I'm giving you this presentation. There actually animations you can run up on your own computer. Okay. So this is the problem. Please read the problem very quickly. Okay. And answer is also here unfortunately because this animation is not working. Okay. Please try to solve without seeing the answer. Okay. I'm giving you just a couple of minutes. Then after I'll explain you this problem, what is going on. Okay. We already have wasted almost 15 to 20 minutes. That is my fault only. Okay. So do you have class after this class? Any other class? Can
No,
anyone
sir.
confirm me?
No, sir.
You don't have. You all. Okay. So can I take
Uh,
15 minutes?
Sir,
Uh,
maybe the naval architecture students must be having a class after this.
okay. Okay. Can anyone of other sections or other departments, can you please confirm me? If you don't have class, I would like to take 15 minutes more. That's what I'm telling. Okay. Okay. So let's continue first. Okay. So meanwhile, you please let me know. So please try to solve the problem one. So please read the problem statement only. Okay. Then please try to solve. Please don't see this particular solution. Okay. So this problem is about simply calculating the work by considering the process PV equal to constant. Okay. So here in the data, P1 is given, V1 is given, and P2 also given. Okay. Now, I'm sorry, by considering P1 V1 equal to P2 V2. Yes, because of P1 PV equal to constant. In that case, P1 V1 equal to P2 V2. Yes. So by that way, we are calculating over here V2. Okay. This is actually what process is this? P1 is 500 kilopascal, P2 is 100 kilopascal. That means expansion process. Okay. So when V1 is zero point 0.1, V2 would be more than that. Okay. That is the reason V2 is zero point 0.5. This is the expansion process. Once this is the expansion process, okay, same kind of your diesel engine when combustion has been taken place, okay, that energy is pushing down the piston. Okay, let us consider that stroke, that whatever the stroke, that was power stroke. From that we use it to get energy. Is it? The similar kind of stroke, let us assume over here. In that case, since work is the path function, we have this formula. Okay, for any case, any process. Okay, W equal to integral V1 to V to PdV. Okay, then this practice we have done in our previous class slides. Okay, so once you solve this, once you integrate it, you will be getting this formula P1 V1 equal to log V2 by V1. Okay, then simply here we have all the data P1 V1 V1 V2. Okay, then substitute these all the things, we are getting 80.47 kilojoules. That means this is the positive value. Okay, that means work output. Yes, work output. Obviously, this is the expansion. Yes, this is the work output. Okay. Now this is the problem number two. It is quite interesting. Earlier case, actually, in problem number one, we have only one process. Okay. Here we have two processes. Okay. Then out of this, please calculate whatever they are asking for. Please read the problem very carefully. I am giving you a couple of minutes. Okay. So this couple of minutes is not sufficient actually to calculate this particular any solution. But however, I am giving you this time to understand the problem and make your own idea how to solve the problem. Okay. So meanwhile, I'll start giving my explanation. I'm coming back in couple of
Sir,
minutes.
what is
Meanwhile,
polytropic compression?
yeah, polytropic. See, what we have considered isobaric, pressure is constant we have taken. Isochoric, volume is constant. And then P, V equal to constant. Isothermal we have taken. Now, upon power of V, certain number is adding. PV power 1.1, PV power 1.3, PV power 1.4. Okay. This power is not whole power. Okay. This is power upon V only. That is actually, if it is 1.3, then we can take it as adiabatic process. Okay. If it is more than that, then we are considering it as based upon this number, the process is changing. That's what we have considered it as general name it as polytropic process. Okay. Okay, I'm coming back in just a couple of minutes. Meanwhile, you please try to understand
Sir,
and
excuse
start your
me.
own. Yeah, yeah,
Sir, I
tell
have
me.
a class from 12 to 1 for breath science and humanism.
Okay, fine, fine, fine. Anyhow, whatever is possible, I'll try to explain these problems and total presentation I'll be giving you. Rest of that, anyhow, all the solution is also we have along with the problem. Then you can try to understand. If any one of you have any problem, then you can type in Teams. Okay, I'll try to complete before 12 o'clock. Because actually 12 o'clock I have another class, that is my elective combustion class. Okay, but yeah, please. If you give me some 15 minutes, that class I can postpone 15 more minutes, but now you have another class, so no problem. I'll stop by 12. I'm coming in 2 minutes, please. Yeah. So could you able to solve? Okay. So here this problem has two process. One is this thing. This is compression process 1 to 2. That is polytropic process. That means PV power n some value. Here n value is 1.3. Okay. Then this is 2 to 3. What is this process? Isobaric expansion. Okay. In both the places, we have to calculate work. Okay. And this problem, whatever, what we are considering over here, P1 V1 power n equal to P2 V2 power n. Okay. So here P1 value given, V1 value given, V2 value also given. So we are calculating P2 value over here. Okay. The P1 value, P2 value. So now P1 V1, P2 V2, both the values we know at both the stages. Okay. Both the states. Now once you go back and see in our previous classes presentation, okay, so there actually we have derived this formula very well. We have derived this formula. Okay, then we are using this formula to calculate work in this process. Okay, and then we are getting the work. This is from 1 to 2. Now 2 to 3. So please keep your mic off. Somebody's mic is on. It is giving some disturbance. Okay, now 2 to 3. 2 to 3 is isobaric process. Okay, for isobaric process also we have derived some formula, that is P2 V3 minus V2. Okay, so through that we have calculated this. Okay. So the net means both the process we are adding. Once you add both, this is the value we are getting. Okay. Yeah. This is about how to calculate work from individual processes. Okay. So now we are going to the first law. Okay. So far we have calculated work calculations for particular processes. Now we are solving a problem about first law. This is again simply whatever we have seen, delta E equal to Q minus W. Okay. So what is this problem? 5 processes are given over here, A, B, C, D, E. In each process, Q, W given. Okay. Somewhere E1, E2 missing. Some data is missing, nothing more. All the cases you will be following this formula. This is very simple problem actually, but however why I have given to emphasize about this particular formula, otherwise nothing. Okay, suppose for the process A, whatever the data is given, I am substituting over here. Q data is given. Okay, heat supplied, this is the positive, heat supplied to the system, this is negative, that means work done on the system. Okay, these two we have substituted and we got 70. Okay, this change in internal energy is 70. Okay, so like this, once you repeat for all the process, the only thing is you have to follow this particular formula and then you will be substituting the given values. Okay, and then you will be calculating whatever these all whatever looking for. Okay, this is very simple thing. And fourth problem. Okay. So please read the problem very well and then please try to solve. After a couple of minutes, I'll try to explain you. Okay. So here, what is happening over here? We have a piston cylinder arrangement. In that, we have certain mass, that is here steam of 5 kg. Okay. Then continuously heat is supplying, that is 80 kilojoules. And also, since this is the heat supply to the system, we are considering it as positive. Okay. And here some pedal work is happening upon this. That means work upon the system. Okay. That's what this is, minus. Okay. Now it is passing between two states, state 1 and state 2. At the state 1, this is the internal energy of much, and at the state 2, this much of internal energy we have. Okay. So now we need to calculate what is the net work output. Okay. So because of this process, this piston may be moving out. Okay. That work may be very much. Okay. And simultaneously, that is work output. Okay. Work done by the system. It would be obviously positive. Okay. And this is work upon the system. It is negative. When you sum up these two, the net work, what it is showing, that we are going to see here. Okay. Now, once you equalize this governing equation, okay, here actually we are not going to see anything what is the expansion process as like your problem number 1 and problem number 2. We are not calculating the work by that way. We are simply equalizing in terms of your first law of energy equation. Okay. See, delta U equal to Q minus W, that we have seen. That is our general formula which we have seen in case of your problem number 3 also. There it is delta E we are considering. Delta E is what? That is summation of kinetic energy, potential energy and internal energy. In the problem itself, we have mentioned that kinetic energy and potential energy we are ignoring. Okay. So that's what only internal energy we are taking. So obviously this formula is actually delta U equal to Q minus W. Okay. So now we are calculating this term. Okay. So once you substitute rest of the values here, M you know. M is what? Mass. That 5 kg is given in the problem. Okay. Then finally we are getting the piston work is 350 kilojoule. Okay. Right. Is combination of mechanics as well as thermodynamics. This you please read by yourself. I am going to the problem number 6. Okay, explanation is given over here. Okay. Now please read the problem number 6.
Sir, your screen is not visible. It's everything blurred.
Whose screen? My screen.
Yes, sir.
Hello. My slide number means problem number 6 slide is not visible.
No, sir. In screen, yes, sir. Now visible.
Now it is visible, sir.
Okay, okay. Now, this problem is about, it has three processes. One is PV equal to constant. Okay. Another process is another equal to constant, and another process is volume equal to constant. In three cases, certain data is given. Okay. So this is the closed cycle. Okay. Then you need to calculate over here the net work output. Okay. So now once you get this net output work value as the positive, okay, what does it mean? We have two kinds of cycles. One is power cycle, another one is refrigeration cycles. The power cycles are giving you the power, okay, and refrigeration or heat pump cycles are taking the power from you, okay, taking the power from you. So that means if you get work output as the positive value, and you can conclude that it is power cycle. If work output is the negative value, then you can conclude it as refrigeration cycle. Okay. Once you calculate, then we will come to know. Let us see. Do you able to see my next slide?
Yes, sir.
Okay. So now this is the problem process 1, 2. Okay. There it has been given in the problem itself. Delta U equal to 0. Okay. Since delta U equal to 0, whatever first law of thermodynamics, delta U equal to Q minus W. Okay. So since delta U equal to 0, Q12 equal to W12. Anyhow, W12 we have to calculate. Here P1 value, V1 value, V2 values are given in your problem. Now P2 value we have to calculate. Same like your problem 1 and problem 2, we are equalizing P1 V1 equal to P2 V2. That way we have calculated P2 value. And again PV equal to constant is isothermal process, means constant temperature process. Okay. Once you derive this by applying integration and these limiting values, okay, then your formula is like this: P1 V1 log V2 by V1. Okay. That way we have calculated work in process 1, 2 is minus 332 kilojoules. Now process 2, 3. What is the process 2, 3? In the problem it is mentioned, it is sorry, isobaric process. Okay, isobaric process. For case of isobaric process, the work output formula is P2 V3 minus V2. Okay, so before solving this, so please refer our previous presentation. Okay, these all derivations and all are given over there. Okay, so that way the work output is 1120 kilojoules. So once you substitute these all appropriate values over here. Okay, now the energy balance for this process 2, 3, obviously delta U equal to Q minus W, is it? That way we are considering over here okay. Now we need to calculate U3 value, okay, or this difference of U1 minus U3 value. Okay, so from the known values we are considering. How we are calculating? So in the cyclic process, whenever we have discussed in our yesterday's class itself, cyclic delta U equal to cyclic delta Q minus cyclic delta W. Okay. So for cyclic process, we have mentioned that delta U equal to 0. Okay. Then there we have taken cyclic process of delta Q equal to cyclic process of delta W. That is there in our previous slides. Okay. So please refer that. By that way, each and every process, this is process 1, 2, this is process 2, 3, this is process 3, 1. Okay. So this is anyhow in the problem itself they have given it is 0. Okay. Then we have equalized it to 0. Why? Because of based upon this. Okay. Then that way we have calculated u1 minus or u3 minus u2 equal to this value. Okay. By holding that, now I have changed the slides. Do you able to see? Okay. Now process 2, 3. Is my slide clear? I'm in the next slide.
Yes, sir.
Okay. In the process 2, 3. Okay. So then again, we have calculated our heat Q. Okay. Fine. Now what is remaining? Process 3, 1 is remaining. What is this process 3, 1? Process 3, 1 is isochoric process. That means constant volume process. In case of constant volume process, since volume is maintaining constant, piston movement is 0. Once piston movement is 0, then there is no displacement, there is no work. That is the reason this work is 0. Okay. So then from your this formula means your first law of thermodynamics, heat equal to delta U. Okay. Then we have equalized that. That is fine. Anyhow, to discuss here whether the cycle is power cycle or refrigeration cycle, only we are depending upon the work. However, at every stage or for every process, we have calculated our heat transfers also. Okay, Q also. But now work in process 1, 2, work in process 2, 3, work in process 3, 1. In the 3, 1, since it is okay, positive value of 787 kilojoules. Okay, since this is the positive value, we are concluding that this cycle is power cycle. Okay, that is about this problem number 6. Okay, so then regarding efficiencies and all, that is very simple calculations. Okay, so here I am putting you one problem over here, that is simply nothing. See, this is the hot body, it is giving heat to the system. Okay, some amount of heat is rejecting, we are getting the work over here. Obviously it is, which cycle is this? Power cycle. Okay, and efficiency equal to work output of the cycle by Q input. Okay, in terms of work output obviously equal to Q in minus Q out. Okay, this formula also yesterday we have discussed. Now every value is given over here. Okay, Q out is given 40 megajoules. Okay, Q out is given you 40 megajoules. Then we are calculating based upon this Q in, we are calculating here. How much is the Q in? Okay,
Sir,
by using, yeah,
sir, here are we considering that this is an isothermal process?
this thing.
Yes, sir.
This thing is, we are not talking about any isothermal process. We are overall talking about cycle only.
Sir, but why we are considering that Q in minus Q out is equal to work then? Because we should also consider the internal energy.
In say cyclic process, in if it is a cycle, then internal energy equal to 0. Change in internal energy
Okay.
equal to 0.
Yes, sir. Okay, okay.
Okay, so that's what internal energy, we don't have any role if it is a cycle. Within the cycle, if you are taking individual process, there actually internal energy role will be there. Cycle itself consists of 3 or 4 individual process you are taking, their internal energy will be there. Change in internal energy would be there. Overall cycle when you are taking, since it is coming back to that position again, okay, net internal energy change is 0. Okay. Okay.
Okay, sir.
Yeah, that way we are calculating Q in equal to this much. Okay. Then work output we have to calculate over here. This work output is giving you, this is simple calculations and we are getting this much. Okay. Anyhow, this is power cycle only. By seeing here itself, we should say this is the power cycle. Okay. And the next thing is, this is the last one, just a couple of minutes. And here what are we doing? We are supplying the heat, sorry, energy, work. We are supplying the energy. Okay. And this Q output is this much. Okay. So this what kind of cycle is this? Either refrigeration cycle or heat pump cycle. But anyhow, this is a cyclic process. Okay. There actually what we have derived, instead of thermal efficiency, we have considered COP, coefficient of performance. Yes, beta we have considered. Okay. So this, according to these calculations, we have calculated even the coefficient of performance is 2. So here, this is actually, we are following SI system. Unit system is SI system. Okay. So we are considering joules and megajoules. Before that, actually, British system is there. BTU. Here everything is given you BTU. BTU means British thermal units. Okay. So here, for your understanding, I am telling here, one British thermal unit equal to 155 joules. Okay, that you please remember. But anyhow, this I am explaining you what is the power cycle, how to calculate efficiency to in or out, thermal input or whatever, energy input. And here this is refrigeration cycle. This one is the power cycle that I am explaining you. Okay. Thank you. So if you have any doubts, please write upon our Teams platform. Okay. I'll be answering you, but immediately may not be possible because we are at home now. Uh, so then I'll answer you just now after this class. I'm uploading this presentation. Okay. So please try to solve problems by yourself. Okay. So each and every line I have added animation. You will be getting step by step animation floating when you are pressing down arrow key. Okay. Thank you. Thanks a lot.
Thank you, sir.
Okay. Thank you. Yeah.
Thank you, sir.